In this paper, we tackle the task of crowd counting. Crowd count is to estimate the number of people in an image. In most datasets, each person is annotated by a single dot on their head. State-of-art method treat crowd counting as a density map estimation problem. The network predicts a 2D crowd density map. The prediction map is dense, while the ground truth map is sparse. During training, how to measure the discrepancy between these two different density maps is important. Almost all previous works convert the sparse point annotation into dense ground truth map. Each point is replaced by a Gaussian blob. The network is trained to minimize the pixel-wise loss between dense prediction and Gaussian smoothed ground truth. However, it is hard to set the right width for the Gaussian blob given huge variations in crowd size. We also proved that imposing Gaussian will hurt the generalization performance. Gaussian is an approximation of real ground truth. The better model fits on Gaussian smoothed ground truth. The poor is generalized to real ground truth. The key insight of our work is to consider density maps as distributions. Optimal transport is a principal way to measure the distance between distributions. We use optimal transport to compute the distance between density maps. We provide tighter generalization bound than previous method and show state-of-art result on crowd counting dataset. In this work, we propose DM count. The main component of a method is optimal transport. We use OT to measure the distance between prediction and ground truth. Since the total mass between prediction and ground truth are different, we first normalize both density map and compute the OT cost between these two normalized density maps. We show the generalization bound of the proposed loss. As the number of data k increases, the expected risk using an empirical minimizer converts to the expected risk using the optimal minimizer. We evaluate our method on 4 challenge datasets. On the largest dataset NWPU, our method reduced the mean absolute error by 17%. Here are results on all datasets. It is worth noting that our method achieves state-of-art performance using a simple VGG backbone network. Here we visualize the predicted density map from different methods. DM count is able to produce more accurate count. A closer look shows that density maps generated by DM count is much sharper, which result in high peak signal-to-noise ratio and structure similarity. In summary, first we prove that imposing Gaussian to annotations hurts the generalization performance. Second, we propose DM count, which uses optimal transport to measure the distance between predicted density maps and ground truth annotations. Theoretically, it has tighter generalization bound. Empirically, it outperforms other methods.